All right, so on number 1, we need to find the coefficient of x. So what is the coefficient? Who will describe a coefficient? Which hopefully is now embedded deep into your heart. Caden.
-5.
Describe what the coefficient is.
The coefficient is the number right before the...
Say it really loud so everyone can hear.
The coefficient is the number before the letter.
That is correct. Or to the left of it, right?
Yeah.
Very good. Okay, and like you said in number 1, the coefficient of x is -5. -5, okay? What about number 2? What is the coefficient OX? Nikolai.
3.
3 is part of it.
-3.
Morgan. It are -3. Remember, it has to take the operation immediately to its left. What about number 3?
Oh.
Morgan?
6.
6. That's very good. What about number 4? Isaac?
10.
No, it is definitely not 10. Addie?
-7.
That is correct. We wanted the coefficient of x.
Oh.
That would be the coefficient OY. Okay? Very good. So remember, when you're looking at these, the coefficient, it's just the number in front of the letter. But it also must take the operation with it. Okay? Like on number 2. So what you're talking about is, for example, like if we had -3 times -5x. Is that what you're talking about? Oh, okay, yeah. In this case, you do have to actually do the multiplication first before you say that -5 is the coefficient, which it is not. You would say 15 is, because you have to multiply those first.
And you do the same thing with division?
Yes, division, yes, but not addition or subtraction because it's separated by the addition or subtraction. Mason? Thank you, Davey. The answer for 18A are 4.
Yeah.
A sequence is an ordered list of numbers. That's it. Hey, that was easy. Each number in a sequence is called a term. In an arithmetic sequence, each term is found by adding the same number to the previous term. Okay? So if you're not adding the same amount each time, then it's not arithmetic. All right? So for example, would this be an arithmetic sequence? Something like this. And then
Yes.
this means it goes on forever in the same pattern.
No.
Nikolai.
I know the answer.
I just need the answer, that's all.
It's adding by 3.
No, I need to know if it's an arithmetic sequence.
Oh, yeah.
It are.
Wait, so... what?
Let's look at another one, like at these.
No.
Is this arithmetic sequence?
No.
What the heck do you mean, no? You get, yes, Allie.
Because it goes 1, 3, and that's 2 away from that, so that's good. And then it goes 3, 5, which is 2 away from that, so that's good. But it goes 5, 8, which is 3 away, so that is incorrect. But
Very good. It became incorrect because you had to add 3 up in here. Okay? The rest of them you're just adding 2. So this one is not an arithmetic sequence. Describe the relationship between the terms in each arithmetic sequence. Then write the next 3 terms in each sequence.
1.5.
So first we need to find the relationship. Okay, so let's describe the relationship. What are we adding to each previous term? Okay, so we have to consider this with the previous term. What are we doing to each previous term? Isaac.
Wait, adding 1.5?
Very good. Add 1.5 to previous term. Bam. The second part of the question is we need to write the next three terms. So after 9.0, Cassidy?
Would it be 11.5?
It would be 10.5. Very good. What's the next one? Jackson? 12th. Next one. Nate?
It's
13.5. Done. Hey, that was pretty rough. Okay. That took a lot of commitment. Okay. All we're going to do is consider these numbers. Okay. This is our sequence. And we must determine if it is an arithmetic sequence.
No.
Okay. Because some sequences don't have to be arithmetic. It can just be a sequence. Okay. So let's look. From 15 to 16, I'm going to use a little bow here. It's very pretty. It changed. Did I add or subtract? I added, because eventually you will subtract. How much did you add?
1.
1. So that means here to here you should add 1, but this one you add 2. Now since these two are not equal, it's no.
But there is a pattern.
Oh, there's a pattern, which makes it a sequence, not arithmetic though. Okay? It's not arithmetic. The explanation, this is good. We showed our work. All right, in an arithmetic sequence, the terms can be whole numbers, fractions, or decimal. Okay? Like they were in the previous example.
$16.
Okay, describe the relationship. So notice in these, what are we doing to each of these terms? We're adding 5 to each previous term. So it's stated here. This is in your book. So to get the next three terms, you take 23 and add 5, right? You get 28 right up in here. 28 plus 5 is 33 plus 5 is
38.
bam, there you go. There's your next three terms. All right, we're going to do the same thing with this one, but again, notice we have decimals, okay? So in this one, what are we adding to each previous term? Cassidy? 0.2. Adding 0.2 to each previous term. Very good. So 1 plus 0.2 is 1.2. Plus 0.2 is 1.4. Plus 0.2 is 1.6. Bam.
We're good at this.
So on this one, these 4 problems, you can do the same thing. Describe the relationship and then find the next 3 terms. Okay? Okay, who will tell us the relationship? Just the relationship in A. Mason.
It's plus 13. So you add 13 each time.
All right, very good. You do need to write that it's add 13 to the previous term, okay? Yep. Just so we know. Because if you say add 13, it'll be like, what? To what? Add 13 to 5. Bam. Okay? So in A, what are the next 3 terms? Who will tell us that? Luke.
52, 65, and 78.
52, 65, 78. Is he good?
Yes.
Yes, he is. Very good. All right, who will tell us the relationship in B? Aubrey?
Add 2 to the previous term.
Very good. Add 3 to previous term. Excellent. So in B, what are the next 3 terms? Allie?
It's 16, 19, and 22.
16, 19, 22. Very good. Yeah, because we're just adding 3 to each term. All right? What about C? What are we doing there? Jackson?
You're adding 0.3 to the previous term.
Very good. Add 0.3 to the previous term. Very good. So who will tell us what the next 3 terms are for C, please? Caden? 2.2, 2.5. And what? 2.8. Very good. And what about D? What are we doing with D? Sierra?
Plus 0.5.
Good. Plus 0.5 to previous term, right? So in D, what are the next three terms? Addie? Oh, Abby. Sorry.
4.5, 5.5.
Sorry, 4.5, 5. Thank you. Oh, very good. You need to consider the position on these things, all right? So, where is it in the sequence? Well, notice 2 has a position of 1, right? That's not a fraction, okay? And this 4 is in position 2. Does everyone understand that's not a fraction? Maybe if I put it up here. So 6 is in position 3. And 8 is in position 4. So, what you should be doing here is considering, based on the position, what do I need to do to the position to get that number? Okay? So in this example, using these 4 numbers, what are we doing to each position? Well, look at this. What are we doing to get from 2 to 4? Add 2, right? What about 4 to 6? Add 2. 6 to 8? Add 2, right? So in this case, if I took position 2, okay, so position 2, make it n. N is the position, right? What would I do to get position 5? To get the value of position 5? Well, you'd add 2 to 8, right? But since we're adding 2 each time, as it turns out, does everyone see that this is just 2 times the position? Does that make sense there? So if I wanted the 20th position, what would I do? Well, you could keep adding and adding forever, and then get the 20th position. But if we use this expression here, we can find it much faster. Okay? So, what is the value of the 20th position? Caden?
20.
No.
What you mean?
The 20th position. What is...
So since 2 is 1, what is
Yeah, what...
20th position?
Yeah, so like 4 would be the value of the second position, right? So what would be the value of the 20th position?
50.
That's very close. Nate?
40.
40. Okay. How did you get 40, Nate?
20 by 2.
Very good. You use the expression 2 times the 20th position. Bam, 40. Very good. All right, just real quick in this example, we can kind of ignore this bottom column. But if we look at this, we can see the first week they sold 5 boxes, and then they're going to sell 5 more each time. So, yeah, you just take 5, and then you'll add the 5 to get the 10. You'll add another 5 to get the 15, and you'd go forever and ever, okay? So what would be the expression for this problem here? Isaac?
5 times n.
Very good. Okay, yep. It's 5 times n. Right? And you may notice that this is position 1. So 5 times the 1 is 5. 2 times 5 and 3 times 5. Okay? So if I wanted to know how many boxes they sold in the 100th week, what would I do? Sierra?
5 times
Very good. 5 times 100. So they sold 500 boxes. Okay? And write an expression for this problem. Now they're not using position, they're using figures. Okay. Well, what expressions do you guys have? Serena?
I did x plus 3.
X plus 3. What does X represent?
How many circles we have in one.
Okay. Now, for these ones, X should be representing, in this one, it'd be the figure, kind of like the position, right? Okay. So, for example, in this one, I would want to take figure 1, right? So I'd say X is 1. Did you say plus 3 or minus 3? Plus. So 1 plus 3 would be 4. Well, there's not 4 in this, there's 3, right? What do you mean?
Well, did you do like, I don't know.
All right. Caden?
I have a question in the
Let's say we're going to use X here, right? X. So X is the figure number, right? Because these must be written in relation to the figure. So X is the figure number. Okay?
wait, so what the mark?
What's that? All right, so she says it's X times 3. Does that work for all of these? Well, let's find out. Figure 1, you'd have 1 times 3, which is 3. That's good. What about figure 2? Well, that's 2 times 3, which is 6. Bam. And figure 3 would be 3 times 3, which is 9, and that is good. Okay? So how many are in the 50th figure?
150.
Nate? 150 circles. All right. Now this was very good because on some years I saw different drawings. I saw someone split these up like this, right? So you can see now that you're adding 3 each time, right? Or there were other ones. It's very, very good. Okay. All right, I'm just going to talk about this real quick. This is what we call an explicit expression. You don't really need to memorize this, okay? But later on, you'll get into 9th grade where they're going to talk about recursive. Okay? In that case, what you would have, well, it's got to be in function notation like this kind of thing. And then you'd say, well, you do, maybe I'll skip that. So let's look at this one again, all right? We know that each time we said, for example, that A, you add 13 every time, okay? What we're going to do is, what you need to do is find the expression for A. Okay? Go back to A. So turn to page 358 and find the expression you need for A. X plus 13. Okay? Let's look. Okay? For the first term, all right, so X
Wait. X.
is its position or term, okay? Or the term. So, that's fine. Hold on a second. Let's just look at this one real quick, okay? So, in the first position, so you'd have position 1 plus 13. This is 14, right? Well, that's 0. So that cannot be the case, okay? But this one didn't work.
X times 13.
Let's try X times 13. Well, in this case, remember position 1 is the value 0, right?
Yeah, but wouldn't that be position
So-
0 if it's 0?
1 times 13 is 13. It looks like X times 13 is a little off there, okay?
X plus.
Alright, okay, well let's see if this would work for the first term, right? So in the first position, plus 14 minus 1 is 14, which is not 0. So just a little off. So. Alright, so Nick says 13 minus X. Let's see if this works. So in position 1, you'd have 13 minus 1, right? Because This is our first position. This should equal 0, right? It's 12. All right, so this is what we got here in this one. 13 minus 13 is 0 for position 1, right? What about position 2? Well, that's going to give you 13 minus 13, which is 0. But position 2 are 13. What do you got?
13 minus 13 times x.
No, that doesn't
Like
work
this?
for 2.
Okay, well, let's check. 13 minus 13 times x. Well, in position 1, you'd have 13 minus 13 times 1. Well, that is 0. What about 13 minus, this is the second position, times 2. Bam, now it's negative 13. But this is positive. All right, so Nate says he's got this one right here, right? 13 minus 13x plus 26. Let's find out if it will work. So we're going to take, in position 1, it should be 0, right? So 13 minus 13 times 1 plus 26.
It equals 26 for position 1.
Yeah, it's 26. All right, 13 minus 13 divided by x. So in position 1, you'd have 13 minus 13 divided by 1. Now this would be 13, so it would be 0. What about position 2? So you got 13 minus 13 divided by 2. So 13 minus 6 and a half. 6 and a half. So it looks like this one, because it needed to be 13, is just a little off. So Heidi says 13 times x minus 13?
Yeah.
Let's give it a shot. Okay, so in position 1, we have 0. 13 times 1 minus 13 is 0. The next one would be 13. Now it's position 2, x. 2 is x. Minus 13 equals 13. Well, position 2 is 13. What about position 3? Let's check it out. 13 times 3 minus 13 equals 26. It's good. What about the fourth one? So we got to check all of them just to make sure. 13 times 4 minus 13. That'd be a 40, 52 minus 13, 39er. It is 39. Does this expression work?
Yeah.
Yeah, it looks like it does. Good job, Heidi.
Not hard
Okay,
one,
so the question is, yes.
oh, jeez.
Heidi, how did you figure this out?
Well, I just thought you needed something that can also equal 0, so I thought, well, if you have 26 minus 13, that would be 13. So I thought, well, if you have 13 times 1, then that would be, minus 13 would be 0.
Okay, interesting. Very, very interesting. Okay. Well, that is very good. So, oh, there it is. Okay. But you're not going to learn it today. This needs to be pointed out, right? So A is 13x minus 13, right? Okay, and some of you were struggling with this minus the 13 part. Okay, that's the part that was killing you, right? Well, in this problem, we knew that we're adding how much to every term? 13, right? Okay, since you know that you're adding 13 to every term, that is how you know what you're multiplying by. Okay, so we could have started this out and said, if you have the term, you're going to multiply 13 by it. Okay? Then after that, all you got to do is say, in term 1, so I've got 13 times 1, what would I add or subtract to this in order to get our first term, which is 0? Well, yeah, it'd be 13, right? So you'd say, well, I'm not going to add anything. I'll just subtract 13. So very good. All right, Allie thinks she's got the expression for b. What do you got?
So I did x times 3 plus 1, and so 1 times 3 plus 1 equals 4.
Very good.
And then I did number 2, and I did 2 times 3 plus 1 equals 7.
Very good.
And then I did 3 times 3, which equals 9, plus 1 equals 10.
Very good.
And then I did 4 times 3 equals 12, plus 1 equals 13.
Now, those are 4 terms here. Looks pretty good, right? So the question is, Allie, how did you come up with this bizarre answer?
So I knew that 4 plus 3 equals 7. And so I got 3. So I got 3, and then I tried adding. So I did 1 plus 3, but that didn't work for number 2. So then I tried timesing it, and then I got it, but I was 1 below. So I added 1 more, and it got it.
There you go. That's very good. Excellent. All right, Caden, what do you got?
X times 0.5
X times,
plus 2.
I'm going to put 0.5. Is that okay?
Yeah.
And then plus 2?
Yeah.
Does that work?
Yes.
It does. This works, okay? Now, I'm just going to point this out because, as a math nerd, you should know this, okay? It's just a notational thing. Some teachers are kind of picky about this. I really don't care because it means the same thing. Most of them would say, you have to put 0.5 in front of the x. Okay? And then you'd add the 2. That's because if I said, what is the coefficient of x in this? Some of you would say 1. Others would say 0. But it's actually 0.5. Okay? It's just a small thing you may need to know in the future. Okay?